Welcome to today's paper reading. Today's paper is titled, Lumiere, a space-time diffusion model for video generation. This paper was published on the AR14 preprint by Omer Bar-Tal and colleagues from Google Research. Lumiere is a novel text-to-video diffusion model designed to address the challenge of synthesizing videos with realistic, diverse, and coherent motion. The model employs a space-time U-Net architecture, which generates the entire video in a single pass, ensuring global temporal consistency. This contrasts with existing models that use cascaded keyframe synthesis and temporal super-resolution, which can struggle with maintaining coherence. Lumiere leverages both spatial and temporal down- and upsampling, and integrates a pre-trained text-to-image diffusion model to produce full-frame rate, low-resolution videos. The model's design facilitates a variety of content creation and video editing tasks, including text-to-video, image-to-video, and stylized generation. Figure 1 showcases the capabilities of Lumiere in generating various types of videos. The first row demonstrates text-to-video generation, where videos are created based on textual descriptions. The second row illustrates image-to-video generation, transforming static images into dynamic videos. The third row presents video in painting, where specific regions of a video are filled in or replaced, as indicated by the bounding box around the in-painting mask region. Figure 2 illustrates the temporal consistency in generated videos, comparing our model, Lumiere, with iMagen video. The figure showcases representative examples of periodic motion, where Lumiere's image-to-video generation is conditioned on the first frame of a video generated by iMagen video. The corresponding XD slices are visualized to highlight how iMagen video struggles with globally coherent repetitive motion due to its cascaded design and temporal super-resolution modules, which fail to consistently resolve aliasing ambiguities across temporal windows. The introduction of the paper highlights the significant advancements in text-image (T2I) diffusion models, which can now synthesize high-resolution, photorealistic images that adhere to complex text prompts and offer extensive image editing capabilities. However, the paper also points out the challenges in training large-scale text-to-video (T2V) models due to the complexities introduced by motion, including increased memory and computational requirements. To address these challenges, the authors propose a new T2V diffusion framework that uses a space-time U-Net (ST-U-Net) architecture to generate the full temporal duration of the video at once, producing 80 frames at 16 frames per second, which results in more globally coherent motion compared to existing models. Figure 3 illustrates the Lumiere pipeline for video generation, contrasting it with the common approach used by previous works. The common approach involves a base model generating distant keyframes followed by a cascade of temporal super-resolution (TSR) models to fill in the frames, with a spatial super-resolution (SSR) model applied in non-overlapping windows. In contrast, Lumiere's base model processes all frames simultaneously, eliminating the need for a TSR cascade and enabling globally coherent motion. High-resolution video is achieved by applying an SSR model on overlapping windows and using multi-diffusion to combine predictions into a coherent result. In the field of text-to-image generation, most approaches utilize diffusion models, such as DAL-E2 and Stable Diffusion. For text-to-video generation, recent efforts have focused on large-scale models using autoregressive transformers or diffusion models. A common approach is to inflate a pre-trained text-to-image model by adding temporal layers. In contrast, our approach generates the full frame duration at once using a space-time U-Net, performing most computations in a compressed feature space to avoid temporal cascades. Figure 4 illustrates the ST-U-Net architecture, which is designed to handle video data by integrating temporal processing into a pre-trained text-image (T2I) U-Net architecture. The architecture includes activation maps that show features from different temporal modules, convolution-based blocks with factorized space-time convolutions, and attention-based blocks at the coarsest U-Net level that use temporal attention. This design allows for efficient processing of video data by compressing the representation at the coarsest level and stacking several temporal attention layers with minimal computational overhead. The Lumiere model employs diffusion probabilistic models for video generation. Starting from Gaussian ID noise, the model gradually denoises the sample to approximate the target video distribution. It can condition the distribution using additional signals like text embedding or spatial conditioning. The framework includes a base model that generates videos at a coarse resolution and a spatial superresolution (SSR) model that upsamples the output to high resolution. The spacetime unit (STUnit) downsamples the input signal both spatially and temporally, using factorized spacetime convolutions to increase nonlinearities and expressiveness while reducing computational costs. Temporal attention is applied only at the coarsest resolution to manage computational requirements. Figure 5 showcases the results of text-to-video and image-to-video generation. Each example is accompanied by a text prompt that guides the generation process. For image-to-video, the initial frame is provided as a condition to the model, ensuring the generated video starts with the desired image. The figure highlights the model's capability to create coherent and intricate video content based on textual descriptions and initial image conditions. The Lumiere model facilitates several downstream applications. For stylized generation, the model uses linear interpolation between fine-tuned and original text-to-image weights to balance style and motion. The interpolation coefficient alpha is manually chosen to ensure both style adherence and plausible motion. In conditional generation, the model is extended to include additional input signals like images or masks, modifying the input tensor to accommodate these changes. This allows for fine-tuning the model to denoise based on the additional inputs. For in-painting and cinemagraphs, the model completes masked regions seamlessly and animates specific areas of an image while keeping the rest static, maintaining the appearance from the conditioning image. Figure 6 showcases the stylized video generation capabilities of Lumiere. By linearly interpolating between fine-tuned and pre-trained text-to-image weights, the model generates videos that adhere to various styles. The results are categorized into vector art styles and realistic styles, demonstrating Lumiere's ability to creatively match different motion priors to each spatial style. This approach allows for unique and dynamic video content that reflects the characteristics of the chosen style. Figure 7 showcases the application of video in painting using Lumiere. Each example demonstrates how the model animates the masked areas of the input video, providing a seamless and natural completion of the masked region, guided by the text prompt. This capability is particularly useful for object replacement, insertion, and localized editing within videos. Figure 8 demonstrates our method for creating cinemagraphs. Given an input image and a mask, our technique generates a video where the designated area is animated, while the rest of the image remains static. Notably, the first frame of the video remains unmasked, ensuring the animated content maintains the appearance from the original image. The T2V model was trained on a dataset comprising 30 million videos, each 80 frames long at 16 frames per second, covering a duration of 5 seconds. The model was evaluated using 109 diverse text prompts and a zero-shot evaluation protocol on the UCF-101 dataset. The evaluation metrics include freshet video distance, FVD, and inception score, IS. The results show that the model achieves competitive FVD and IS scores, indicating its effectiveness. Additionally, a user study revealed that the model was preferred over all baselines in terms of visual quality and motion, demonstrating better alignment with text prompts. This highlights the model's capability to generate high-quality videos with significant motion while maintaining temporal consistency. Figure 9 illustrates the application of SDEdit for video-to-video editing using our model. The figure showcases the ability to generate full frame rate videos without the need for a temporal super-resolution cascade, thereby enabling straightforward downstream applications. The first row displays several frames of an input video, while the corresponding edited frames are shown below, demonstrating consistent video stylization achieved through SDEdit. Table 1 presents a comparison of zero-shot text-to-video generation methods on the UCF-101 dataset. Our method, Lumiere, achieves competitive freshet video distance, FVD, and inception score, IS, when compared to other prominent text-to-video, T2V, diffusion models. The table highlights the performance metrics of various models, demonstrating Lumiere's capability in generating high-quality videos from text descriptions. This evaluation is crucial for understanding the effectiveness of our method in the context of zero-shot generation tasks. Figure 10 presents the results of a user study comparing our video generation method to several baseline methods. The study reports the percentage of user votes in favor of our method, blue, and the baseline methods, orange. Users preferred our method in both text-to-video and image-to-video generation tasks. The baseline methods included in the comparison are Imagen Video, Pika, Zeroscope, Animate Diff, and Gen 2. This study highlights the superior performance of our method in terms of user preference and alignment with text prompts. In this study, the authors presented a novel text-to-video generation framework that leverages a pre-trained text-to-image diffusion model. They identified a limitation in the current approach of generating distant keyframes and interpolating them, and addressed this with a space-time UNet architecture. This design directly generates full frame rate video clips by integrating spatial and temporal down and upsampling modules. The framework demonstrated state-of-the-art results and applicability across various applications such as image-to-video conversion, video in painting, and stylized generation. However, the method is not capable of generating videos with multiple shots or scene transitions, which remains a future research challenge. The principles of this model are also applicable to latent video diffusion models, potentially inspiring further research in text-to-video model design. The primary goal of this work is to empower novice users to create visual content in a creative and flexible manner. However, there is a significant risk that this technology could be misused to generate fake or harmful content. Therefore, it is crucial to develop and apply tools for detecting biases and malicious use cases to ensure a safe and fair use of the technology. Additionally, a user study was conducted to compare the image-to-video model against several baselines, including Pika, Stable Video Diffusion, and Gen 2. The results indicate that the method was preferred by users in terms of video quality, highlighting its effectiveness. Thank you for watching.